All right, hello and welcome to another class. We have been looking at the chemistry jam syllabus, considering topics by topics, and new topic, and the title is solubility. Solubility is the topic that we're looking at today, and for those of you that are just joining us for the first time, I would like to introduce myself. Your teacher, your tutor, whatever name you want to call me. My name is simply Anjorin Oluwafemi Excel. I have a BSc in chemistry from the University of Ibadan and a PGD in science education from Federal College of Federal College of Education Technical, Boca. I also hold a master's in environmental and analytical chemistry from Redeemers University, Ede. And I'll be your teacher, your tutor, and your guide in this topic, solubility. Let's start off by looking at our lesson objective. The lesson objective for this class is, by the end of the lesson, students should be able to do the following. Number one, distinguish between the different types of solutions that we have, interpret solubility curves, calculate the amount of solutes that can dissolve in a given amount of solvent at a given temperature, deduce that solubility is temperature dependent, also relate nature of solvents to their uses, differentiates among true solutions, suspensions, and colloids, and compare the properties of a true solution and a false solution. And finally, provide typical example of suspensions and colloids. Okay, without wasting much time, let's jump into the lesson for today. The first thing that we need to do is to define some terms, and I've made out certain technical terms that we need to look at and also their definition. So we'll look at them one after the other, and we will talk through them. The first definition is solution. A solution is formed when a solute dissolves completely in a solvent. That is a homogeneous solution, where we have a solute plus solvent equals to a solution. So a solution is simply a mixture of two or more substances. So when you have a solute that is dissolved completely in a solvent, for the case of a homogeneous solution now, we'll refer to that as a solution, okay? So you have the solute, you have the solvents, then you have the solution, okay? The next thing that we need to look at is the solute. What is the solute? This is defined as the substance which is in a smaller amount in a solution. For example, if you mix 40 cm cube of water and 20 cm cube of ethanol, from the simple definition above, water becomes the solvent, while ethanol becomes the solute because it is in a smaller quantity. Another instance is when sodium pellets dissolves in water or other liquids. Of course, the pellets are the solute, while water is the solvent. So we've also established a definition for solutes as a substance which is in a smaller amount in a solution. Okay. The next thing we need to also define is a solvent. And we say a solvent is one of the components of a solution. Usually, the component is greater in quantity in the solution. So when two or more substances are mixed to give a homogeneous mixture, one will be in greater quantity to dissolve or overshadow the other. This component that is most often in greater quantity is called solvent, while the other that is in lesser quantity is called the solute. Okay. All right. So the next thing we need to also define is saturated solution. Saturated solution. Say saturated solution is simply a solution which contains as much solute as it can dissolve at that temperature in the presence of undissolved solute and particles. So it contains as much solute as it can dissolve at that temperature in the presence of undissolved solute. So we refer to that as a saturated solution. Okay. Another definition that we need to talk through is supersaturated solution. A supersaturated solution contains more solute than it can hold at that temperature. It contains more solute than it can hold at that temperature. Example, when you have the syrup, when you have honey, sugar content is so much, more than what it can contain at that temperature. When you have carbonated drink, where you have the CO2, it is more than what it can contain at that temperature. And that is why often when we open a carbonated drink, what you see is a like, because the carbon is pressured inside. Not only that, it is more than what can be contained in that particular, temperature. All right, the next thing we need to look at is unsaturated solution. And we define unsaturated solution as one that does not contain as much solute as it can dissolve at that temperature. So it can contain more solute. That's just the implication. So it does not contain as much solute as it can dissolve at that temperature. Example, sugar in water. When you just add sugar, a little sugar in water, you can still add more. So you say it's still an unsaturated solution. Then we have salt in water. Also, hair is an example of an unsaturated solution. Okay, having talked about that, then we need to define solubility itself. Solubility could be defined as the maximum amount of salts, that is solutes, that will saturate 1 dm cube of the solvent, water, at a given temperature. And that is what solubility is, the maximum amount of salt or solute that will saturate 1 dm cube of the solvent or salt or water at a given temperature. All right. So solubility of salts in water. Now, the rules for solubility of salts is as given below. All common salts of sodium, potassium, and ammonium are soluble. They are all soluble. Number two, all triazocarbonate 5 salts are soluble. All triazocarbonate 5 salts are soluble. Number three, all common chlorides are soluble. All common chlorides are soluble, except those of silver and lead. However, lead 2 chloride is soluble in water on warming. The next one is all common tetrasulfate 6 salts, except those of calcium and barium, are soluble. Okay, and the final one is all triazocarbonate 4 salts are insoluble, except those of sodium, potassium, and ammonium. Okay, I want to establish those rules regarding solubility of salts. Let's move on to the next slide now. Okay, solubility curve. The first thing we need to do is to define what solubility curve is. And based on this definition that I have here, you say solubility curve is a graph that is showing how solubility changes with temperature for a specific solute in a solvent. It's a graph. It shows solubility, how solubility changes with temperature for a specific solute in a solvent. So you have a solute temperature, axis, and then you see the changes as the case, as it goes on like that. Okay. So the axis in the solubility curves basically are the x-axis, that is for the temperature in degrees Celsius, and then the y-axis, that is for the solubility in grams of solute per gram of solvent. Also, we need to talk about the shape of the curve. Solubility generally increases with temperature for most solids. So when we have an increase in solubility, temperature also increases, so that is for most solid anyway. So that's we'll be looking at the shape of the solubility curve very, very soon, and you see the trend that as solubility increases, the temperature also increases. Okay, exception: solubility of gases decreases as temperature increases. So this is the only exception when we have to talk about solubility of gas. But every other substances like liquids and solids and all that, this particular statement holds true. Now, interpretation of points on the curve. Points on the curve represents saturated solution at specific temperatures. Now, when you have a point above the curve, this indicates supersaturation. So when you draw the curve and you have points above the curve, it indicates what? Supersaturation. When you have points below the curve, this indicates what unsaturated solution. Okay. Now, the solubility curve is used to predict its application now. Is used to predict how much solute will crystallize upon cooling. It's used to determine or to predict how much solute will crystallize upon cooling. Now, real-life use includes the use of designing cooling system or cooling processes in crystallization industries. Okay. All right. So that's that for that concerning solubility curve. The next thing we need to look at is plotting solubility curve. How do we plot solubility curve? That's the next thing that we need to look at. Now, we'll use these as an example. Look at the solubility of potassium KClO3 in 100 grams of water. Now, if you look at it, these are the solubility, as we can see. These are the solubility on this of KClO3, and then this at the temperature, just like what we said earlier. As solubility increases, temperature will also increase. It's a direct relationship, and you can actually see that playing out in the table that is right there that we are looking at, you know. So if you want to draw a curve for this, the curve will look like something this way. The curve will look like this. Let's see. Okay, so this is how the curve will look like. Let me take myself out of the equation. Okay, so the curve will look like this. You have the solubility on the vertical axis, and then the temperature on the horizontal axis. And for each of the points, what we do basically is that we look for the points for solubility, and then we trace it down to where we have the temperature, and then we mark it out. And that is what you do basically. And then you now try to the best of your ability, join the points together and join them together in their centers like that. So this is how we do the plotting of a simple solubility curve. So what you see basically is how to plot a solubility curve, just like what you have there at 40. It's a 0 degrees Celsius. If it's at 40, it's 0 degrees Celsius. You can see that's 40, 0 degrees Celsius. And then you look at it again at 50, it is 10 degrees Celsius. And looking at that, you see at 50, it is 10 degrees Celsius. So you just keep picking the points and plotting them accordingly. And that's how we plot a solubility curve. Okay. Now, plotting solubility curve, still a continuation. I have just brought out a particular question, and then we'll try to sorry, not a question now. From the graph that we just plotted, the curve that I just walked us through, this particular curve, there are some questions that was drawn out. So like take for instance, from the graph plotted, determine the solubility at 35 degrees Celsius, 38 degrees Celsius, and 50 degrees Celsius. So now when you look at it at 38 degrees Celsius, at 50 degrees Celsius, the solubility corresponding, you see solubility at 35 degrees Celsius is 100. And then the solubility at 38 degrees Celsius is 115, and that at 50 degrees Celsius is 160, based on based on our graph and based on what we have in our graph there. Okay, so the question says determine the temperature at 145 mole per dm cube. So at 145 mole per dm cube, the temperature should be about 46 degrees Celsius. And if you trace it, you will actually see, when you trace it down, you can see what the temperature would look like. So that is how we plot a solubility curve. The second example says plot the graph of the solubility of two salts with the given data below. So this is the data that we have for two salts, and then if you plot the graph properly, and I want you to attempt it also where you are, so that you'll be sure that you're getting it. If you plot the graph very well, what you will end up having will look like what we have in the next slide, like this. So these the two sorts will take this form, and that is how to plot the solubility curve. Now from the graph in the previous slide, at what temperature is the solubility of K equals 0.5 mole per dm cube? Now, if you look at it closely, you discover that the answer is at about 39 degrees Celsius. Yes, at 39 degrees Celsius. So if you look at it, you can actually trace it down and you see that it's at around that 39 degrees Celsius that we have that. Okay. And it says, read off the following from the graph plotted in the previous slide above. At what temperature is the temperature of L equals to 53 degrees Celsius? 53 degrees Celsius. So we look for the mark on 53 here. If this is 0, we can say this is 2, 4, 6, 8, 10. Okay, so this is 20, 30, 40, 53 should be in between here, and when you trace it back up there, you get what the solubility will look like. And so the solubility, you can read it off from the graph. It says determine the solubility of L at 10 degrees Celsius. So what you just need to look for is 10 degrees Celsius, and then look for the solubility at that point. And this is it here. When you trace it back, you have this. So that's the solubility of, okay, sorry, it's L now, pardon me. So it's of L at 10 degrees Celsius. This is the intersect. So you trace it back to this and you read out what is there, and then you have the solubility at 10 degrees Celsius. Okay, having said that, now let's look at some calculations involving solubility. The first one, the first question says that if 50 grams of calcium trioxocarbonate 4 saturate 500 cm cube of water at 60 degrees Celsius, calculate the solubility of the salt at that temperature. And the first thing we ask ourselves is that we're given 500 cm cube of water, and it is saturated by 50 grams of calcium carbonate. Now, okay, if that is the case, what if what we have is 1000 cm cube of water? Because don't forget that what we are looking at is solubility in what's it called? We need to convert that 50 gram to gram per dm cube. You know, so if 500 will contain 50 grams, what will 1000 cm cube of water be able to, you know, saturate? And when you do that, what you have is just 100 gram per dm cube. Therefore, we can now bring in the formula that says solubility in mole per dm cube equal, excuse me, please, equals mass in gram per dm cube over molar mass of calcium carbonate. We can calculate the molar mass of calcium carbonate. So we can calculate the molar mass of calcium carbonate from the parameters given, from the relative atomic numbers that was given to us. Once we had all the relative atomic numbers together, we have a molar mass of 100 gram per mole. So we bring in that into the formula of solubility in mole per dm cube, which equals to mass in gram per dm cube over molar mass of calcium carbonate. So that will be 100 gram per dm cube divided by 100 gram per mole. When we do the division, the solubility in mole per dm cube equals to 1.0 mole per dm cube. Okay, I hope that is clear. I think that is pretty straightforward. But if you have a question or you're confused regarding what I just explained, just put it in the comment section. I'll look at it and respond adequately to it. Thank you. All right, let's move along now and look at the second one. Second example, it had been observed that 40 grams of sodium hydroxide saturates 100 cm cube of water at 50 degrees Celsius. Then calculate the solubility of sodium hydroxide at 50 degrees Celsius. So we're given the relative atomic numbers of sodium hydroxides and sodium rather, oxygen and hydrogen. Okay. So there's the relative atomic masses of those ones were given to us, so it will help us in calculating the molar mass. But one thing that we must look at first and foremost is that 100 cm cube of water is saturated by 40 grams of sodium hydroxide. Now, I want to bring this also back to dm cube. So we now say that what with 1000 cm cube, because 1000 cm cube is equivalent to 1 dm cube. So what will 1000 cm cube of water, you know, what mass will 1000 cm cube of water be able to saturate? So we have that as 40 divided by 100 times 1000, which will be equals to 400 gram per dm cube. Now, bringing back our formula, like we stated earlier, solubility mole per dm cube equals to mass in gram per dm cube over molar mass, okay, of sodium hydroxide. So we can calculate the molar mass by just adding up the relative atomic numbers or relative atomic masses, and then we have the molar mass to be 40 gram per mole. Okay, having said that, we can now fix that into our solubility formula by saying that solubility in mole per dm cube equals to 400 gram per dm cube divided by 40 gram, and that solubility there will be what? 10 mole per dm cube. Okay, all right. All right, now let's look at some activities. Is it activity? I think I put some activities, but before the activities, let's quickly look at the third example now. 400 grams of a saturated solution were found to contain 80 grams of the solid solute at room temperature. What was the solubility of the solid at room temperature? Okay, now the first thing that we must establish, we've talked about that in our definitions of term earlier, that when we have a solvent and a solute adding together, it will give us a solution. Now, the solvent, we don't know the quantity. The solute in this case is 80 grams of solid, and then the solution, the resulting solution, the saturated solution that was formed, is contains about 400 grams. Okay, okay, it's 400 grams. Now, based on that, we can actually bring in that formula says solvent plus solute equals to solution by saying that solvent, which is unknown, plus 80 grams of the solute equals to 400 grams of the solution that was formed. Now, don't forget that X is the mass of the solvent. Now, we collect like terms, and X will be equals to what? 400 grams minus 80 grams, then X will be equals to 320 grams. Now, this implies that 320 grams of the solvents dissolved 80 grams. 320 grams of the solvent dissolved what? 80 grams. Okay. Now, the question now is 1,000 grams. What will 1,000 grams of the solvent now dissolve? 1,000 grams of the solvent will dissolve 80 grams divided by 320 multiplied by 1,000 grams. And that will give us 250 grams of the solute per 1,000 grams of the solvent. Okay. All right. So that is that's concerning that. Now let's look at let's take a close look at the next one, which is the class activity that I said I put together for you. I want you to carefully look at the class activity and ensure that you attempt it. It's important that you engage with this question. So please carefully look at them and ensure that you attempt it. Even if you don't get it right, it's better to attempt it and you know where the problem is, and then you can solve it, accordingly. So please look at all the three questions as in your class activity and solve them. After you've solved them, you can come back to this and then put your answer in the comment section. I will look through it and I will react to the solutions provided accordingly. Okay. All right now. So having said that, let's move on now as we look at the other slide now. We want to look at solvents for fats and oil. Solvents for fats and oil. So solvents are substances that dissolve other materials to form a solution. Now, in chemistry, specific solvents are used to dissolve fats, oils, and paints, making them useful in cleaning and stain removal. The ability of the solvents to dissolve a substance depends on the principle of like dissolves like. Like dissolves like, meaning that non-polar solvents dissolves non-polar substances, such as fats and oil, while polar solvents dissolves polar substances. Okay. Now, fat and oil are primarily non-polar substances, meaning they are insoluble in water but dissolve readily in organic solvents. Now, common solvents for fats and oils include 1. Ether. Ether is a non-polar solvent that dissolves oil and fat effectively. It is used in laboratory setting for fat extraction. Another organic solvent that can be used in dissolving fat and oil is benzene. Well, this is now replaced with safer alternative due to its toxicity because benzene has been linked to carcinogenicity. It is carcinogenic, so it can cause cancer. That's the meaning. So most times now, we now try to replace it with safer alternatives. But nonetheless, benzene will dissolve fat and oil And because it's the strong organic solvent for oils and greases, and previously it is used in dry cleaning, but now avoided due to the health risk of using such. Okay. All right. Hexane is another substance that can dissolve fat and oil. It is widely used in solvents for extracting vegetable oils from seed and found in industrial degreasing application. Chloroform is another non-polar organic solvent that can be used for dissolving fat and oil, and it is used in laboratory for fat analysis and has been replaced by safer solvents in modern application also because it's also a bit toxic and it can also be harmful to the health. It has also been replaced by safer solvents. Okay, macetone is another example, but if chloroform will be used anyway, it should be used with care and with the necessary precautions taken. Now, acetone is another solvent that can be used for dissolving fat and oil. It dissolves oils and greases quickly, and it is used in cosmetic like nail polish remover and so on and so forth. Now, solvents for paints. Now, paint contains pigments and binders and solvents. When removing paints, solvents dissolves the binder and breaks the adhesion of paint to surfaces. Now, common solvent for paints for paint removal includes number one, turpentine. It's a natural solvent derived from tree resin. It is used in oil-based paint thinning and cleaning brushes. Okay. White spirit, which is the mineral spirit, is a petroleum-derived solvent used for thinning oil-based paints. It is also commonly used for cleaning paint brushes and surfaces. Okay, acetone is another wonderful solvent that can be used for paint, toluene, and also methylated spirit. That is the denatured alcohol. Okay, all right. So what are the uses of solvents or use of solvent for stain removal? Solvent that are used for use of solvent rather for stain removal. Number one, removal of oil and grease stain. Acetone, hexane, or ether can be applied to fabrics, that's clothes, on surfaces with oil stains. Rubbing the stain gently and blotting it with a clean cloth helps lift the oil. Washing with detergent afterwards ensures complete removal. Paint stain remover, turpentine, like we said before, denatured alcohol, and alcohol-based solvents, and so on and so forth like that. So these are solvents that we use for stain removal. Okay. All right. Safety precaution when using solvents. When we use solvents, it is important that it is used in well-ventilated areas to avoid inhaling toxic fumes. Number two, wear gloves and protective clothing to prevent skin irritation. And the next one is avoid using flammable solvents near open flames or heat sources. Also, dispose of solvent properly to minimize environmental pollution. So these are safety precautions that we must take note of when we are using these solvents. Okay, now the next thing we want to look at is the true solution, so to speak. A true solution is a homogeneous mixture where a solute is uniformly dissolved. A solute is uniformly dissolved in a solute is uniformly dissolved in a solvent, forming a single phase. So that is what a true solution is a homogeneous mixture where a solute is uniformly dissolved in a solvent, forming a single phase. Examples of true solutions include salt dissolved in water, sugar dissolved in water, and air, which is a mixture of gases. Now, what are the characteristics of a true solution? Number one, particles are very small, less than 1 nanometer. Another characteristic is that it do not scatter light. So there's no Tyndall effect with a true solution. Number three, it cannot be separated by filtration. You cannot separate a true solution by filtration, okay? The next one is it does not settle out on standing. It does not settle out on standing because it's always an homogeneous solution. It forms a single phase. Okay. I haven't said that now. Let's look at colloids now. What are colloids and what are the characteristics of colloids now? If you look at it closely, colloids can be defined as a heterogeneous mixture where particles are dispersed throughout a medium, but are not dissolved. The particles are dispersed throughout the medium, but they are not dissolved. Example of colloids include fog, water droplets dispersed in air, milk, fat droplets dispersed in water, aerosol spray, liquid or solid particles dispersed in a gas, and emulsion paints, pigment, and then rubber solution, rubber particles dispersed in a solvent. These are examples of colloids. And now, the characteristics of colloids include the following. Number one, particles are larger than in true solution. So 1 nanometer to about 1,000 nanometer. That's the size of the particle. It exhibits Tyndall effect, which unlike the true solution, colloids exhibit Tyndall effect, that is, it scatters light. Number three is that it cannot be separated by filtration. It cannot be separated by filtration. And then finally, it does not settle out on standing also. Okay, all right. So that's that for colloid. Let's look at suspension now. Now, suspension is defined as a heterogeneous mixture where particles are dispersed throughout the medium, but are not dissolved and are large enough to settle out, you know. So you can be looking at some of the differences between a colloid, a suspension, and a true solution. But I'm going to still show us a table trying to look at the differences, you know, just just using the table. We're going to look at that very, very shortly. So that is what a suspension is a heterogeneous mixture where particles are dispersed throughout the medium but are not dissolved and are large enough to settle out. Examples of suspensions include one, Harmattan haze, dust particles suspended in air. Number two example is water paints, pigments suspended in water. Then muddy water, sediment suspended in water. What are the characteristics of suspension? Number one, particles are large, greater than 1,000 nanometer. That's the particle of the suspension is large, very, very large. May or may not scatter light, but often appear opaque, you know. Also can be separated by filtration, unlike what we have in the true solution and in colloids. And particles settle out on standing. So these are the characteristics of suspension. Okay, let's do a comparison now. A comparison between true solution and false solution in quotes, you know. In chemistry, the term true solution refers to a homogeneous mixture where the solutes completely dissolves at the molecular or ionic level in the solvent, resulting in a single phase system. That is what a true solution is. Now, the concept of a false solution is less commonly used and not a standard term in chemistry. However, it can be interpreted to describe mixtures that appear homogeneous, but upon closer examination are heterogeneous, such as colloids and suspensions. Okay, all right. Having said that, let's move on now to the next one. Okay, now when you look at this is a true solution and then a false solution. Example, colloids and suspension. So I want to do what I call a differentiation, or yes, based on certain properties, you know. Look at the definition. We've acted on this or so much. I've talked about this so much, but I'll still talk about it again now. And if you look at the definition, homogeneous mixture, that's the true solution now, is a homogeneous mixture where solid particles are completely dissolved at the molecular or ionic level, forming a single phase system. Now, false solution or colloids or suspension, on the other hand, are a mixture that appears homogeneous to the naked eye, but it's actually heterogeneous with dispersed particles larger than those in true solution. Okay, now in terms of particle size, we can also make a differentiation by saying that a true solution has less than 1 nanometer. The size, it's the size of the true solution. Particles in a true solution, they are less than 1 nanometer. But for colloid, they are 1 nanometer to about 1 micrometer, and suspensions are greater than 1 micrometer. Okay. Based on the appearance, again, we can also differentiate. True solution are clear and transparent. Particles are not visible, and the solutions are the solution does not scatter light, no Tyndall effect with true solution. So for solution or colloids or suspension, may appear cloudy or opaque. Particles can scatter light. That's Tyndall effect and may be visible under the microscope. Okay, all right. See, now let's look at the next one now. The next differentiation is along stability now. For true solutions, they are thermodynamically stable. The solute particles do not settle out over time. Yes, they do not settle out over time. And then for colloids and suspension of force solutions, so to speak, for colloids, they are relatively stable. Particles do not settle rapidly, but may over extended periods, they may settle out. For suspension, on the other hand, they are unstable. Thermodynamically, particles tend to settle upon standing. Now, let's differentiate based on filtration. Now, for true solution, particles pass through standard filter paper and semi-permeable members cannot be separated by filtration, okay? For colloids and suspension, colloid particles pass through standard filter paper, but are retained by semi-permeable membranes. For suspension, particles can be separated by filtration. Now, when we want to do a differentiation also based on Tyndall effect, we'll see that true solution does not exhibit the Tyndall effect. They don't scatter light. Light pass through without scattering. For solution, they exhibit Tyndall effect. Light is scattered by dispersed particles, making the light part visible. Okay, so that's that for true and false solution. So let us quickly try and summarize what has been taught so far. Now, we've tried to look at solubility. We've defined what solubility is. We've also touched on solutions. We've mentioned different types of solutions that we have: the saturated, the unsaturated, the supersaturated, and so on, okay? So we have touched on that in the course of teaching, and we've also touched on I think solubility curves and the application. Yes, solubility curve and the application. We have looked at that also. We have defined solubility curve as a graph showing solubility on the y-axis against temperature on the x-axis. We've also tried or attempted to interpret what points on the solubility curve, what it implies or what it represents. We have talked about when we have points on the curve, it represents a saturated solution. Point above the curve indicates supersaturation, and then points below the curve indicate what? An unsaturated solution. We've talked about the application of solubility curve, and we also touched on true solution. We've defined what a true solution is, their characteristics. We've looked at a false solution, so to speak, that is colloids and suspension. We've defined them. We've also looked at their characteristics also, okay? So these are some of the things that we have looked at in the course of today's lesson. And yes, we talked about solvents that dissolves, fat and oil, different solvents and the ability to dissolve fat and oil. We have talked about the fact that solvent will dissolve, solute or substances that have equal property with them. That is, a polar solvent dissolves a polar solute or stain, so to speak. And then for a non-polar, the same thing happens. So we've touched on that, and we looked at things like turpentine, ether, benzene, chloroform, and so on and so forth like that. Okay, so these are some of the things that we have been able to look at in the course of this lesson, and I hope you have you understood all that I've been trying to explain so far. But if you have any gray area, that is, if you have any points that you don't really understand or you're not so clear about, or you need more explanation, you can just put it in the comment section. I will look at it and respond accordingly to it. Thank you very much. So let me evaluate this class, or this lesson rather, by using the following question. The first one says that, which of the following best defines solubility? So we have defined solubility. What I want you to do for me now is that, which one do you think best defines solubility? So you would look at the options that we have there, and anyone that you feel is the right answer, put it in the comment section, and I will look at it and respond accordingly to it. Whether you're right or not, I will let you know. The next one is that what is the effect of increasing temperature on the solubility of most solid solutes in water? The options are there, so please look at the options, pick the right answer, or pick the answer that you feel is the most suitable and put it in the comment section, and then I will look at it and let you know if you're right or not. Okay, a solution that contains more solute than it can normally hold at a given temperature is called what? Is it a saturated solution, a supersaturated solution, unsaturated solution, or dilute solution? Okay. Which of the following solvent is commonly used for dissolving fat and oil? We've talked about this. So look at the options and then give me what you feel your answer is. Okay. All right. So these, look at that calculation there. You can also attempt it. Very good one. So attempt it and let me know what your answer is in the comment section. Which of this solution will exhibit Tyndall effects? Okay. So look at the question, the options carefully, and let me know which one you feel will exhibit Tyndall effects. Now, the next one says that which of the following gases has increased solubility in water at lower temperature? So pick on which one you feel is the right answer and put them in the comment section. All right. Thank you so much for listening and watching. And I hope you gained something valuable in the course of this teaching. I'll stop here for this topic, and I'm going to continue with another topic. So please do well to stay on the channels, do well to, to join on later for another topic that we're going to be looking at in the chemistry jam syllabus. Thank you once again for listening. I'll see you in the next one. Okay.